Meow.
Hey everybody. Might be having a special guest today. That special guest is my printer printing a 4-hour print in the background, which isn't really a long print, but it's a long print for my printer. That's about the most long print he's ever done is 4 hours. And he needs to do a 6-hour one later today, so everybody wish him luck. I'm wishing him luck. Hello! How's it going? Wait, let me... I got my sad music. This is how I feel when I see I need to do a Navier-Stokes equation. Sniffle sadly. You know what the real sad thing is Rev is streaming right now, and I wish I could watch Rev stream, but I was like, you know what I'm gonna do? I'm gonna stream today early because I want to watch Dungeon Meshi later with a friend. And I was like, well, I want to stream today. So, you know what? We're here with our pitiful little sad music. Instead of watching Lick Beetle's awesome Hypnos... I'm so mad. That game is so good. I kind of want to play it over the summer. Me just stealing Rev's content. If you don't know Rev is part of a little... I want to say streamer group, but like it's not like official or anything, but me and Chlamidity and Click Beetle are all friends, and we hang out and we talk to each other. Anyway, enough weeping and crying and sniffling. Fourier series. So I did this one with a lot of pain. I realize I am not very good at getting these right on the first try, which, hopefully we can fix that. I mean, I'm getting better. It's just I keep making mistakes that I wish I wasn't making because there's a lot of... God, there's a lot of little things that just, if you get one thing wrong, you're borked. The one thing I don't know that's weird is every single time, and I think this... Hi, Damie. How's it going? 64. I get the intercept wrong every single time, and I don't know why, because I'm doing it correctly, and it's just not the correct intercept. So we're gonna have to look into that. I'm fine. And you? I'm good. You know, I'm excited to start my morning with some Fourier series. Oh, Ukrainian Chell. Sorry. 555. Hello, how's it going? We're doing some Fourier series. Speaking of, maybe we should get our little dude out on the table here. None of these are particularly hard. It's just that they're a little involved. Gotta go? Oh, no worries. Thanks for stopping by. 0. Okay, so we have 0, and we have X, and we have 1. So we'll have to draw it out, but let's see, from -2 to 1, and then from 1 to 1. Oh yes! A symmetric interval! Yes! Oh my god, yes! Oh my god, yes. You guys have no idea how much of a dub that is. Or maybe you do, and you're like, yes, you're cheering alongside me. Wow, that's awesome. Okay. Cool, so let's draw this out. So we can see what it looks like. Just a classic little function, you know. Nothing too out of pocket. Okay, so we got 0 from -2 to here. And then we have X. Oh, it's gonna be so beautiful. It is actually a little... Oh, wait, no, there's a discontinuity here. So we'll do that. His X is like this. Like that. And then we have 1, so it's continuous here, which is cool. Hi, Damie. I'm about to go to Micro Center. Ooh! There's not a Micro Center, like, around where I am right now, so it's pretty cool. I like going over the summer with my friend. He likes it, and I just like to go around and look at stuff because I think it's fun. I like to see their funny, goofy 3D printers. What are you going to Micro Center for? Alright, so Well, okay, if we look at this function, is it even or odd? Nope, it's neither, so we're gonna have sines and cosines, so we gotta do the whole 9 yards. It is just lovely. 1 over L, negative L to L of f of x dx. And then we just gotta do that. Okay, so our L in this case is 2. Or I guess I should say, like, our period equals 4, L equals 2, and really get that cemented. 1 over 2 times, and then we'll just break this up into the 3 integrals. Well, so 0, I'm not even gonna bother with. There's no area there. And then x is symmetric from -1 to 1, and x is, it's an odd function. Yes! Yes! Oh, the world rejoices. Odd. Yay! 0. That's gonna make our integral so much easier later. So we basically only have to do one integral that's just a constant, which is awesome. Plus 1 to 2 of just 1. Ah, yes. Okay. 0. And then we'll have... Okay, so we can just kind of do a little geometry. And 1 times 1 is 1. So, I mean, you can integrate and just be like, well, 2 minus 1 is 1. But also we can just say 1/2 of 1, it's a square. 1 times 1. I probably shouldn't write x. When are you going to introduce us to freaky math? What do you think is freaky math? Like, what kind of... Okay, tell me what, like, freaky math is, and then I'll tell you what kind of math is freaky math, and I can introduce you to it. Like, what are the characteristics of freaky math? Because, I mean, I have some math I think is freaky, but I don't know if that's a shared... Hi, hope you're well. I saw you were on, just wanted to say hi. Oh my gosh, thank you. So niceys of you. I need to, like, over the summer, I wanna lurk more on people's streams. Need to get on top of just paying attention to people. 0, yes! 0 goes away! Oh, and cosine, yes, it goes away! I love odd functions so much. I love symmetric integrals so much. God, it's so beautiful when I don't have to do the work at all. Oh my god. Odd times even equals odd. That deserves 3 exclamation points. And then we have to choose 1. Lurking intensifies. Have a good lurk. Also, freaky math is like not 69 plus 69. That is like the most tame math you can get. That's just a number. That's like, you can count to that number. I feel like the freaky stuff is like, I don't know, like imaginary numbers. That's kind of up there. Oh, and this is just cos n pi x over L. Yes, it's so easy. Let's go. It leads me to believe the other one was hard for no reason. Maybe there was something easier I could do there. Well, it wasn't actually that hard. There was just like 2 by parts. Okay, so we get 1/2 times the integral of cos, so that's going to be sine n pi x over 2 times 2 over n pi, evaluated from 1 to 2. And we have to be a little careful. One check, sine, derivative, yeah. This is the part where I tend to go wrong every single time, plugging these numbers in. So we get sine, I'm gonna just write it out, sine n pi times 2 over n pi. Sine of n pi is 0, and then minus, we're already going off the rails, minus sine n pi over 2 over n pi. Okay, so that is where... This is our term that's gonna stay. We need to keep this boy. I'm not gonna... So n pi over 2 is like... 0, 1, 0, -1, which you could write as -1 to the n. But I'm gonna leave it as this just because I feel like it makes me make less mistakes. Because you could say -1 to the n plus 1 because there's also a negative right here. But I'm gonna leave it like that. Because every time I try to turn it into -1s, I'm just like, man, I don't like my life right now. Because my Fourier series is not going well. I love when you plug it in and it just makes like the most like garbage thing known to man, and you're like, well, I can't add numbers together. That's definitely what this is. Okay, so the 0 goes away. The x is not going to go away because it is an odd times an odd, which is an even, unfortunately. But we can pull out a 2, and we can do from 0 to 1 of x sine n pi x over 2. And this is like an odd times an odd equals even. I'm so glad that like this class like just kind of taught us about symmetric intervals, because I mean I knew about symmetric intervals like kind of intuitively, but it's just such a cool thing to be able to have in your back pocket. Sine n pi x over 2. Whoops, I don't know why I put L here. I put L there too. What? Let's put 2 in there. Dx. I have a midterm quiz on Friday. Fuck. Oh no. Oh no. It's fine. I just have to like do all the projection stuff too, and so I have to rememorize all that. There's so much, this class is full of so much random stuff that you just have to memorize like the process of, which I kind of hate because it's like, I mean, it's really important stuff, but like, I don't remember all of it, man. I gotta do fluids. What am I gonna do? Like, okay, x sine x, we'll have to do by parts for that, so we'll do that real quick over here. X, 1, 0, sine, cosine, sine. Okay, cosine, sine, negative, negative, positive, negative, positive. I don't need that one, but this is n, 2 over n pi, 2 over n pi squared. So I kept forgetting those as well. Okay, so negative x cosine n pi x over 2, 2 over n pi, plus sine, whoa, I don't know what happened there, sine n pi x over 2, 4 over n squared pi squared. Clean, nice, beautiful. And then we just have to integrate this one. That one is going to be plus... Oh yeah, and this is actually from 0 to 1. And also it's multiplied by 2. Actually, I'm going to just leave the 1/2 out. And I'll just pull the 1/2 in front of that. 1/2, what is this, cosine? Negative cosine n pi x over 2, 2 over n pi. Yeah, okay, I just wanted to check to make sure I didn't goof anything up there. Alright, now evaluation time, also the worst part. Okay, so if we have 1, we get negative cosine of n pi over 2, 2 over n pi. Which... that's 1. So this is the weird one, because like for cosine, it goes... Both of these have like zeros in them, so I don't think we can just like it's different if it was like 2 n pi over 2 plus 2k pi plus k pi. Then it would just oscillate back and forth between this for sine, and then it wouldn't be an issue. But like for cosine, it's sometimes 0 and it's sometimes 1, so we're just gonna leave that. And then plus sine of n pi over 2, 4 over n squared pi squared, minus, okay, 0, that goes to 0, and then sine of 0 is also 0. Plus, okay, this one is gonna be, let's see, I'm gonna leave the cosine of n pi again. Just gonna leave it like this as well, it doesn't really matter. negative cosine of n pi 2 over n pi minus, so plus, cosine of n pi over 2 over n pi. The 2's are going to cancel out, so we'll just do that. I'll pull out the n pi. I'm so what's the word when you... I'm indecisive, that's the word. It's like, what's the word when you can't decide? Indecisive, there we go. Alright, well, so that's our Fourier series. Is it right? I don't know. Who knows? Okay, let's try it. Oh, I'm nervous. Oh, I'm nervous. I don't know. It's not going to work. See. Okay, Desmos it up. Here we go. So our A0 was 1/2, so it's going to be 1/4 because we divide that by 2. We need a sum from 1 to, let's just say 10. And that's going to be of our... Oh boy. Okay. Negative sign. Okay, so 1/2. It's a negative. Negative 1/2. Sine of n pi over 2. Two over n pi times cosine of n pi x over 2. Oops. 0. Okay, so that's not bad. That's some of the behavior we want. Let's see, so what's the rest of it? Sum 1 to 10. Oh, and this is the long-ass one. Okay, God damn it, this is gonna take a while. You think I could just call them A and B? Let me try this. Let's try this, just so I can at least input things in a little easier way. Let me get rid of this for now. Hello, Paper Mario. Pi over 2. N squared. Pi squared. Okay, we got something going on here. All of this is going to be multiplied by something. 1 over n pi. Cosine n pi. Over 2? No, cosine minus cosine n pi. This looks promising. Plus cosine of n pi over 2. This does look actually kind of promising, is the thing. And then, all of this times... Oh boy. I'm gonna copy that just in case it goes haywire. Times cosine... Nope, sine. N pi over 2. Uh-oh. X. N pi x over 2. Okay. Now what if I say plus A? Wait, is that our function? Wait, that kind of looks like our function is the thing. Wait. Is that actually our function? Wait, low-key, that might be our function. Holy shit. Wait. That's our function. Oh my god, we got first try? First try Pog? Wait, what? Oh my god. No way. Damie does it again. Damie does it for the first time. I've not gotten this right on the first time ever. Wait, that's so poggers. Oh my god, it just... These are really cool. They are really cool. I think it's like crazy how you can just, and if we like bump it up and my computer doesn't hate me too much, it like really gets right there. Or if we zoom out a little bit too, maybe not. Sometimes it'll actually like show you the points that it's at properly. It's pretty cool. I like that we can also say plus A. That's nice. Oh yeah. Wait a second. I can do that thing. We say this is like K. Oh, it's not gonna like understand. I think it's crashing. Yeah, if we say like step 1 and we say from 1 to I don't know, like 10, then we can see that it gets closer and closer to it. Or wait, let's do, yeah, like 1 to 20. Look at that. Isn't that so cool? It goes pretty fast. Like, that's... I mean, in terms, compared to infinity, 20 is very small, and that's pretty decent approximation, even with only 20. And like, if we go to like 100... Like, whoop! Convergent AF, yeah. Like, really after... about 30, like 25, 30 terms, it just kind of pretty chills out. It's so cool. Oh, I can't believe I got it. That's actually kind of crazy. Okay, one thing, we just have to draw the... We have to draw the actual Fourier series for it, which is gonna be basically the same picture, but we just have to draw some dots in the middle of stuff. Wait, it's asking for -8 to 8. Okay. My printer is just trucking over there. Okay, let me draw a straight line. Oh my god. There we go. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. I don't know why I always put like such a bigger distance here. This feels right, I say. It's like, don't touch the middle. I don't know. Okay, so our initial one was sort of like this. And then that -x. So now all of the intervals are sort of going to be open. Well, not all of them, I lied. Some of them are going to be closed. This one's going to be closed. But then this goes down. Wait, no, that one's not going to be closed. Anytime it jumps, we're going to put one in the middle instead. So like at 0.5, there's going to be one. And then I think it repeats like this. Oh god, my poor printer. I can hear him. A really big part. I'm printing something for my friend, so... okay. Got that. Kind of a pretty little function. Oops. I really shouldn't have made tick marks. It's really hard to see the... I think you can see. I think you get the picture. There we go. And then here. And like that. And I feel like I'm a robot right now. Sorting algorithm. Kind of tedious. Why did he give us such a big interval? Bro, I gave you 4 periods. You don't need that many. Okay, there we go. Greedy period. The period enjoyer. That's the Fourier series. You guys should probably write it out too. I don't want to write this out. We'll write it out later. Write out. Please. Future me is gonna hate that I have to do that. Okay. Oh boy, okay. Okay, we need to I know, oh my god, this is like a lot. We need to find the Fourier series of cos x from negative pi to pi, and then cos x from negative pi over 2 to pi over 2. So 2 different intervals. I'm kind of I really should be doing fluids, but I'm kind of avoiding doing it because I really need to, like... Oh, the differential analysis is just hard. Because, like, they don't really teach us anything, which, you know, I wouldn't be mad at in some cases, but also I'm mad at. It's like, you have to know about boundary conditions, you have to know about all these things. I'm like, guys, you realize, like, we never did this in anything. Like, it's hard to find because so many of the problems are so simplified that it's like, when people are solving them, they're like, ah, well, these aren't even really worth, like, talking about. So it's like... Okay. Negative pi to pi. Alright, I mean, I guess we can just draw a cosine. Probably a good idea. Pi over 2 pi. Pi over 2 pi. 1, negative 1. Cosine at 1 is 1, and then cosine at 0. Cosine of pi is negative 1. Okay, good. I was like a little worried there. I was like, get my axes out of the way. Get out of here. So, I guess the question is the Fourier series going to be the same? I think it might be, actually, because we're probably going to be approximating it with sort of a... I mean, it's a symmetric kind of thing, like... But maybe not. Maybe not, we'll see. We should only have cosines. We shouldn't have any sines. So, that'll be easier. Okay, so a sub 0 is going to be 1 over... So our period is 2 pi. L is our half period, that's going to be pi, so 1 over pi from negative pi to pi of cosine x dx. This is going to be, it's an even function, so it's 2 over pi from 0 to pi cos x dx. Even. And that equals, let's see, sine of pi, I guess just sine of pi minus sine of 0, huh? That's 0. Wait, what? That shouldn't be right. That's not right. There's area under... Oh wait, no there's not. It's from pi to pi. I was looking at 2 pi. There shouldn't be area, should there? I mean, I guess I can just say it's 0 by inspection. And then a sub n. So we're gonna have a sub n's. As previously, just gonna... That's our x cosine x. No. Cosine x times cosine pi... Oh, power reduction. Or is that true? Not power reduction, actually. Oh, just nx. Well, it's even, so let's just start by that. We can at least make it a little easier. From 0 to pi, cosine x. There's an identity that I don't remember, so I'm gonna look that up. Good thing to know. Here's my math here. Yep, it's here. I don't know why I want to look for it. Sorry, let me just check this one thing that someone is. Okay, nothing important, never mind. So often that is the case. Because you just need to walk into a river instead of checking your emails. What was I looking for? I was looking for, oh yes, the cosine rules. Ew. Big identities, who likes those? God damn it. Okay, this is actually gonna be a little scuffed. Alright, so cosine A times cosine B is... I hope he gives us... I don't think he can... There's no way he cannot give us these as a thing, because I think he said that he doesn't know them. And he's not the kind of guy to give us something that he doesn't... to make us memorize something that he doesn't know. 1/2 cosine A minus B, so x minus nx, plus cosine A plus B, x plus nx. It's quantity 1/2. Oh, okay, so whatever. This can cancel out with that. Alright. Getting somewhere. So cosine of x minus nx is cosine of... This is x1 minus n, and this is x1 plus n. So... let's see, that becomes... sine of x... or, I don't know, it's weird to write it like that. It's kind of wacky to write it like that. X 1 minus n. I don't like how many parentheses there are. What's it doing? Oh yeah, 1 over 1 minus n plus sine. I mean, I guess this is just our thing, our thingy. Do I have to worry about the n pi? No, because our interval. And then 0 to pi. Which... let's see, so for x equals pi, I mean, I don't know, it's just gonna be like pi's and stuff. Except for the zeros, so sine of 0 is 0, so it's just gonna be pi. One over 1 minus n plus sine. What a funny little function. We should probably check if this is right before we do anything else, because I have a feeling it's maybe not. But hey, you know, maybe I'm just a doubter. There shouldn't be any. I'm gonna say no, only even. No signs. No sins, no signs. Less work to do? Alright, let's check. Oh, here we go. I don't know why I covered my case later. Whatever. How do we want to do this? So it's gonna be 0. It's really just a one sum. So from n1, I'll do k again. Turn that off, and then what do we have? We would sine. Wait, there's signs in it though. Okay, maybe we're already wrong. But maybe not, maybe not. Maybe I'm being a hater. I'll hold my judgment. Oops. Okay, maybe I can just do this. I have a better idea. Sine, pi 1 minus n plus sine pi 1 plus n times cosine n pi x over pi was our half period, so just nx. Well, that is certainly not right. That's a line. Yeah, because sine of pi is going to be 0. What? Did I do something wrong? Well, definitely, I did something wrong. I don't know what I did wrong, though. Well, I mean, I guess that makes sense, otherwise I wouldn't have done it wrong. It's gotta turn into sines, like, they're cosines, so, I mean, any way you slice it. Huh. You can do it over this interval, right? I wonder maybe if it's like you can't do it over... But yeah, that's not... There's nothing where it's like, oh, for a Fourier series, you can't do it over this interval because we don't like it. Like, no, it's not. You can do it over wherever. Well, not wherever, but like, this is not an interval that would be... Maybe, let me just check on an integral calculator real quick. There's not really much point to doing this without me, like, at least trying to see what's up, you know? What am I doing? Okay, it's just cos x, cos nx. Probably not gonna like me doing that, but let's see. It's like, man, this shit. Oh, interesting. No, that is what I had. So it says sine n plus 1 times x. Apparently there's a 2 in there, though. Oh, because, yeah, we canceled out our 2. Music stop. There we go. Good music for this. Yeah, you see, yeah. Let me put in the bounds, maybe. Maybe that'll help. Help even out this case. That turns into negative n sine n pi. It's gonna be 0. It's straight up just gonna be 0 is the thing, because sine n pi is 0. Huh, interesting. Well, I guess maybe we just check it over, if period equals pi, L equals pi over 2. So A0 equals 2 over pi, negative pi over 2, pi over 2, of cos x dx. Okay, so we get a sine x. Let's see, sine of pi over 2 plus sine of pi over 2? Wait. Minus, no, sorry, minus, I'm gonna just do this. Which equals, let's see, sine of pi over 2 is 1. And then sine of negative pi over 2 is negative 1. So 4 over pi. Yeah, I think. Does that make sense? Because sine is an odd function, so if you pull it out, you have to pull out the negative, so then it would be positive, and then yeah. Alright. Getting somewhere. And then an, I mean, we're still not gonna have any, like, odd behavior, so we don't have to worry about that. So 2 over pi. Well, I can just copy this sort of from that. Wait, 2 over pi. Oh, wait, sorry, I did it from... Oh, shoot. Well, yeah, I'll just do it from 0 then. I think it's just, it's just 2 over pi, I guess. Sorry, double counted. Yeah, 2 over pi from 0 to pi. Then cosine x, cosine nx, dx. And this funky little guy, I kind of squished it there. I'll just do this. I love doing these little funny swirly guys. I feel like it's so... This makes me happy. I never realized how, like, musical my printer was. It's very, I think it's because its belts aren't, like, perfectly clean, but it makes these, like, very interesting musical notes when it's moving around. Okay, what are we doing? I forgot. 2 over pi from 0 to pi, and then we have cosine, I guess, of x n plus 1. Sorry, n minus 1? Oh, it doesn't matter. Plus cosine of x n plus 1. Yeah? Yeah, you see? Yeah. Oh, and there's a 1/2 in there. Oh, I gotta put Star Fox Adventures. Nice handwriting. Oh my gosh, thank you. Wait, that makes me feel awesome, because mostly people hate my handwriting. Let me fix this. I'm like self-conscious. There we go. Getting a little squished. We have to do like engineering lettering and stuff. My lettering's okay. I don't know what I would letter. Like, okay, radius. Cool. It's a diameter, it's not a radius. Okay. This goes away. 1 over pi. And we get the same stuff, different day. Oh gosh, hi Stocky, how's it going? My integral went to 0 and I don't know if it's right or not. It feels wrong. This one I think is right though. I'm getting sines and I shouldn't be getting sines, I should be getting cosines. Oh no, I don't have any space. Oh, what? Oh wait, 1 over 1 plus n. Okay, let's see if this is right, if this gives me anything. Because the other one gave me a big fat line. Oh, that's the integral calculator. This one is so woeful. It's just a line at 0. So piteous. Basically, all we're doing is changing this to pi over 2. I don't know why I did all the math for that. Literally, all we're changing it to is pi over 2. Like... Wait, it didn't change it at all, though. What the heck? No. What did we do? What did we do? Oh, no. Okay, which part of it is the 0 part? That's the 0 part. Yep, that's the 0 part. Why is it 0? Oh, wait. It wasn't 0. Oh, that's so funny. It just wasn't 0. I just Oh my god, that's so stupid. That's so stupid. Oh my god, that's so stupid. Why is it 0? Why is it 0, guys? Oh my gosh, this one's not 0 either. Wait, no, it is 0. It is 0. This one makes sense that it's 0 because it's pi. But pi over 2, it shouldn't be 0. Okay, good. That doesn't look like cosine. That looks like the opposite of cosine, actually. Can I make k like 100? Whoa, okay, that also doesn't look like cosine. What are we doing, gamers? What did I do? This is not cosine. Wait, n pi x over 2. That changed it so much. I think it might be 2? I think it's 2n pi x, actually. Oh, that makes it worse. That makes it definitely worse. This does not look like a cosine. It's not even going from 1 to -1. Where did we go wrong? What's happening? I think it might be time to ask our good friend a question. No, this is the same thing. I don't. Wait, look, this, like, is right, is the thing. Wait, did I... From 0 to pi... Oh, wait, okay, sorry, 0 to pi over 2, let's try that. Our good friend integral calculus... Oh, boy, okay, Okay, no, it's fine. That is what we got. That's what we got. It's like the frequency domain representation, yeah. This is something I would find the f sub c value for resonance of. I don't know why it looks like this at all, actually. I feel like there's a lot of things that went wrong. Well... where do we look? Where do we go? What do we do? I don't know. Wait. Okay, I think I figured it out. I think I figured a lot of things out. First off, okay, so that's one thing that I think is, possibly causing it. I don't know why this is like that. Yeah, that's better. That's correct. I don't know why... Where's this? What is this parentheses doing there? Oh my god. We had a sine inside our cosine, I think. Or sine inside our sine. Okay, that's fine. I don't need this, though. Really. I don't think. Okay, so that's fixed. The other thing that we just don't have is this. That I just didn't write. So this might help out a little bit. Or it makes it 0, or it just makes it not show up. Okay, sure, that's also good. Okay, this might be Desmos just freaking out. Hey, Desmos, you want to render that? Maybe you don't want to render it with such a high K value. You want to render it for anything? Oh, it doesn't like that at all, actually. Ooh. Okay, what if I don't do that? This is a really nice foyer series we got going on here. I really like this one. I don't know what to do. I think we need to reload this, but I kind of am sad that I have to get rid of these. Let me do this. Give me a second. Okay. Okay, it just straight up isn't loading, actually. Okay, what if I just, like, copy it, and, like, I paste it, and I get rid of K, and I just say, like, 10. Maybe it's the K that's I'm copium, it's definitely not the K that's making it do this. I'm forever fighting Desmos and GeoGebra. I read that as I'm forever fighting demons in GeoGebra, and I was like, yeah, that makes sense. That is the same thing. I don't know what's wrong, though, is the thing, which is frustrating. It looks fine, but I just put in 1 plus n and it hates me forever. Oh, wait! Sorry for yelling at you. Oh, that's a 1 minus n there. Oh, it doesn't like the minus n. What if I did... Okay, that's weird that it doesn't like that. Oh, maybe because... Okay, well, first off, this is the first thing. That is what it's supposed to be. Okay, we're getting somewhere. And then... Well, okay, let's look at it, what it looks like with this. Maybe it looks slightly better with this. I think it's something about when n equals 1, it's like... The domain is borked, so what if we just start at n equals 2? There we go, baby. That's how we get them. Okay, it's not exactly right, but I think this one needs to be 2. Wait. Okay, so that's not right at all. Where's pi over 2? Yeah, so that's not right, whatsoever. But I'm guessing it's a period thing, and there's certainly a shift thing going on. Oh, wait a second, our a probably isn't gonna be, our a0 isn't 0 anymore. Oh, it's 2 over pi, yeah, okay, so it's gonna be 2 over pi, so it's 1 over pi. 1 over pi. Plus. Okay, so we fixed that, sort of. There's an amplitude issue. Maybe this is 2 over pi? No. The 1 over pi... This is probably like if I put more values, then it gets close. Yeah, okay. Let's do 30. Okay, so it's going pi over 4, which leads me to believe that I think we... Wait. Wait. No. I was thinking, because our period, no, our period is pi. It's not. Our half period is pi over 2. It's kind of there. I mean, it's not there at all, but it kind of is. It, like, needs to be moving faster or something. I'm just gonna set k equal to 0. Or, sorry, k equal to 30. And put this at k. I don't know. I don't know what that amplitude issue is. What if I said 2 pi? Well, that's smaller. That's not good. What would I have to have this at? Would it be 2? And then this would be 2? Huh, okay, so that's like more right. Which, does that make any sense in the math, if that is what it is? That's like if we said that there's no... So we got a 2 from our symmetric interval, which is good. And then... we canceled out that 2 when we did our product to sum calculation. But... oh, wait a second. There was a... no, that's not gonna be it. Let me just try and massage it, you know what I mean? I change this to like 4. No, okay, so it's not the period, I don't think. I don't really know what else it could be other than the period. It looks like it's not... what if it was sine of pi? No, never mind. No, not sine of pi. Not sine of pi, not sine of pi, not sine of... No. Oh, wait. That's right. That's right. Okay, why is that right now? Okay. Our period is pi, but our L should be... but it's n pi x over L. So it should be 2n x over pi. No. Wait. Right? But that's like so close. That's definitely right. But why? What if I did 2nx over pi? No, that's not right. Because it's n pi x over L. So the pi's will cancel and you're left with this. You're left with 2nx. But it's not supposed to be 2, it's supposed to be n. Why? It's so mysterious. I mean, well, it's not mysterious. That's the only thing that's weird to me about Fourier series is, like, I feel like half the time I do them, I'm getting answers that are off by a factor of something that, like, is close, but, like, it's not close. I don't know, it's weird. It's really weird. Like, am I missing something in my equations, maybe? Let's see. Let me just, like, double check. So, it's a0 over 2. So, in this case, it's gonna be 1 over pi, which we have, which is good. Wait, was that what we had? No, we had 2 over pi. And 2 over pi is right. Why is it 2 over pi? It's supposed to be 1 over pi. What? Like, see? That's what it's weird. That's what's weird. Wait, okay, wait. Maybe it's not 2 over pi. Maybe it is 1 over pi. And then I say, like, wait, sorry, let me go back here. Maybe it's 1 over pi, 1 over pi. But then it's like nothing is scaled properly. I feel like clearly it's supposed to be 2 over pi. Like, the whole thing is multiplied to 12 over pi. The whole thing is multiplied by 2. Like, every single thing, except for these. This is the weirdest one, though. Like, the cosine 2... Like, if you have cosine 2... It's not even like we're saying, like, cosine of x, though. You know, it's not like... that. This is so weird. Okay, I'm gonna star this one, and we'll figure it out some other time. Because I don't know what's going on. I don't know what's going on, and it's stumping me, and it's scary. Okay, so we've been doing these for about an hour. Should we do the demons? I think we might need to tackle a true demon. I'm so nervous, man. It's scary. It's scary. Differential analysis is so scary because I'm not gonna get it right. Okay. Be kind to me. Be patient with me. We're gonna venture into the breach. Oh, thank God that cropped it. That has my name on it. I forgot to turn off my headings. There you go. The breach. Doxing myself. Oh, I can't. Okay, we gotta do a book problem. We gotta do a book problem because I don't think I'm ready. I don't think I'm prepared. Let's see first though what wait, let me do this. Sorry. This, that. Here we go. I don't screw myself over. Let's see what other problems. Maybe there's a more like gentle introduction to it. I say, as it's literally differential analysis. Wait, that's an example problem. Ooh. Ooh, exciting. No, I'm kidding. We're not gonna do that. We're gonna do these. Okay. I'm kind of behind on my fluid stuff. I gotta catch up on it a little bit. Okay, so there's only 5 problems, and we were working on 3, which is not like the most behind actually, so that's fine. Even though I was supposed to have them done a long time ago, it's fine. I just have to get them done before the final, which is a crazy thing to say. I definitely shouldn't say that, but like, these are scary. These are scary. Let's just take a look, and then we'll see. I'm actually gonna put it like, I'm gonna put it like this, so it's less scary. Everybody just, if we all turn our head to the side, then no. Okay. Okay, a pitot static tube is used to measure the speed of air at standard atmospheric conditions at a point in a flow. To ensure the flow may be assumed incompressible for calculations of engineering accuracy, the speed of the flow should be limited to approximately what value? Easy question. Less than the speed of sound. No, sorry. It's speed of sound over, let's see, so V over speed of sound, V over C is to be less than 0.3, so V is less than 0.3 C. Our Mach number. If the pitot-static tube is connected to a water-filled U-tube manometer, what is the manometer deflection in millimeters H2O that corresponds to the limiting speed in A? Oh god, okay. Pitot-static tubes are commonly used to measure velocity in flowing fields. Yeah. Spend some time reviewing the theory behind the use of a pitot-static tube for playing golf now, for velocity measurement. Yeah, so we use basically a pitot-static tube is like a little elbow of pipe, and there is a stagnation point right here that the fluid, it measures the static pressure of the fluid, i.e. the pressure in the fluid as if you were moving with the fluid, and then it measures the what is it called? The other one. I don't remember what the other one's called. The other one, and then basically the difference between these two is the dynamic pressure, and the dynamic pressure is your like viscosity velocity squared. That's not true. It's density velocity squared, I think, is your dynamic pressure, and then you can back out essentially from the readings of these. You can hook it up to a U-tube manometer so that it creates like a pressure difference between the two, and then you can read the velocity. A lot of fluids demonstrations use it. Like if you see, there's some old, like if you're looking at like nozzle flow stuff, if they have like a nozzle setup, you'll probably see they have these like little kind of manometers like sticking up, and the manometers are basically pitot tubes that, so you can see the relative velocities without having to do like a simulation or anything, which is cool. Okay, I guess we could do this. Why not? Let's take a crack at it. So the pitot, so let's draw it first. That's a good. Let's draw a schematic. We have a pitot-static tube. I erased the one that I drew, but it's fine. And it's connected, so it's connected to a water-filled U-tube manometer. I don't really know how it would be connected. Let's find if we can. Let's see, pitot-static tube with manometer. Ah, okay, so it's like this. Don't look at this. Well, okay. You know what? It might be fun to do it up. I feel like everybody does it down, but it's okay. It doesn't really matter. It's like this. Oh, can I draw curves? Oh yeah, I can. Is this gonna actually work if I do it upside down like this? uh, maybe not. I think it's okay. Basically, you have, like... Is this right? Let me think. Yeah, it'll work, it'll work, it'll work. No, it won't work, I lied. I'm sorry, chat, we have to do it this way. So the fluid doesn't fall out. Let me make it a little bit shorter, okay. I don't know how this is a differential. Oh, it's probably Bernoulli's, never mind. Okay, so this is our H. Huel. Alright, so... let's start with the... I mean... I don't know. Let's start with what H is. We're gonna need like a pressure difference. So delta P... Or I guess we could say like P1 minus P2. I should probably label... This will be 1 and this will be 2. So P2 minus P1. The pressure is higher at 1 actually, so it'll be P... no, it's fine. Negative equals rho GH. Oh, I guess we say rho 1 G1. Well, we've assumed that it's incompressible. Now, steady flow is an interesting one. I'm gonna leave it blank for now, but we'll come back to it, and it's probably gonna be steady, but, you know, just in case. We definitely know that it's incompressible, though, because we're below our Mach number 0.3. Rho G H1 minus rho G H2 equals rho G. So H equals negative P2 minus P1 over rho G. Now, the question of whether we can find... I mean, the P2 is going to be atmospheric pressure. And then we just need the pressure here. That's an interesting question of what that pressure is, I think, before we try and look for it. And so we know our velocity, that's our one known. Which means we'll be able to say what the dynamic pressure is, but we need to figure out how a pitot tube works. So let's spend some time reviewing the theory. It's covered in the assigned reading. Okay, we're gonna go on a trip to textbook land. is the only PDF editor I could find that was free and that let me write on it, so that's why I use it. It looks like I got really mad at the end of that word. Yeah, so P0 is the stagnation pressure. So we are getting the stagnation pressure. Maybe there's an example. Okay, yeah, here we go. Here's literally an example of exactly what to do, which, you know, we don't need that, but like, we could, it's okay. Okay, writing Bernoulli's equation across the stagnation streamline with z equals 0 yields PO over rho plus P over rho plus V squared over 2. So we'll write out the full Bernoulli's equation that cancels stuff out. Let's start with that. Let's see where we can get with that. I don't want to spoil the whole problem, you know? Sorry. Did I spell an... Wait. No, I spelled analysis right. I was like, did I only put one A in analysis? Okay, Bernoulli. Bernoulli's EQ says that P1 over rho 1... Oh boy, I don't remember off the top of my head. I'm sorry, Bernoulli. Where's my boy Bernoulli at? Bernoulli's equation. It was like the only thing we used in physics when I took it in high school when we did fluids. It was 1 over 2 rho V1 squared plus rho GH1. Oh, we have to draw a streamline, so we'll go and do that. It's incompressible. Okay, so streamline. I guess 1, 2? Is that like how they did theirs? They didn't draw a streamline? H2, and then P1 minus P2 equals 1/2 rho V2 squared minus V1 squared? I feel like they did something more. Oh, they're using, so... Wait, are they saying that the pressure is constant? No, they're not. They're saying P over rho plus V squared over 2 plus GZ. PO is the stagnation pressure at the tube opening where the speed has been reduced. Equals constant? Why are they saying that? They're saying that because... let me see. That's so weird. I guess what they're just saying is like... Wait, but that's so weird. Well, okay, maybe it's not that weird. What they're just kind of saying is like... They're just mushing things around. Yeah, it's a question of I don't know what I'm solving for. So let's write this with the P0. So our P0, I'm just gonna call them P stagnation and P whatever. So P stagnation plus 1/2 rho times 0 squared, because that's when our velocity is 0. V stag, we'll just call that 0, equals P static plus 1/2 rho v2 squared. So then our p stag, or let's solve for a v2. Square root of, got it, okay. Oh, okay, wait, no, we're chilling. We're chilling. P static minus p stag, sorry, p stag minus p stat, times 2. 2 over rho. Right? Plus or minus? Let me see if that's right. Wait a second. Yes, okay. I get it. I haven't worked with Bernoulli enough, I'm sorry, my boy. Okay, so now we just need this difference, and this difference straight up just is what our manometer reads. So I'm gonna move this down. We're trying to read the height though. Or, oh, wait a second. We don't want to solve for that. I lied. We want to solve for... God damn it. I want to solve for the difference in the pressures. P stat equals P dynamic. Oh, yeah, it's 1/2 rho v2 squared. Okay, well, yeah, I did extra work, I think. I don't really need to... But to be fair, I did extra work here, too. This is not true. This is p stat minus p stag. Sorry, p stag minus p stat. This is, H. What is this? This is like pressure equivalency? Or I mean, I'll just say hydrostatics. That's what it is. And then, minus... It shouldn't be minus. Should it? It should be positive. Wait, but V... I guess I don't really need a, Okay, that's what it is. And then, like, the trick would be to, you know... Oh, let me write it like this. Rho v2 squared over 2 rho... Wait, is that the same rho? This is the rho of the liquid. Oh no, this is the rho, that's the rho of the manometer? Right? Rho fluid. Rho water. It's in... but it's in... Well, I guess I should say fluid. And then the rho GH, this is rho manometer. Yeah, so we can't cancel them out. Fluid. Rho fluid, and then, yeah. Cool. Alright, that wasn't too bad. That also wasn't really... that wasn't really too much differential, although I mean, technically it was, but... I'm more concerned about Navier Stokes. I think we gotta get on that. Okay, we'll do that one problem with the... I gotta go and read this stuff though, too. I think it's just because I've been kind of avoiding wanting to do the Navier-Stokes stuff because it's just hard, and then I didn't really want to think about anything because I was like, well, I need to finish Navier-Stokes first. And it's like, yeah, but, like, don't dwell. Okay, Oh my gosh. Follows, holy shit. Thank you, Weed and Sun, and for not, FemVox fan. Me when I'm a bad streamer, I'm sorry. I got so excited about my fluids. Okay, I'm scared. I'm scared of this. I'm so scared, guys. Like, actually. Okay, let's just get used to this problem. Dip our toes in, if we will. A liquid flows down an inclined plane surface in a steady, fully developed laminar film of thickness h. Simplify the continuity and Navier-Stokes equations to model this flow field. Obtain expressions for the liquid velocity profile, the shear stress distribution, the volume flow rate, and average velocity. Wow, that's a lot of stuff. Relate the liquid film thickness to the volume flow rate per unit depth of surface normal to flow. Wait, where's that? It's that one meme where it's like, great, I can't make that joke. That's like a crazy joke. But the guy was like, "Can you send me all these pictures of yourself?" This is what this feels like. Calculate the volume flow rate in a film of water. Okay, that's fine. That's just using it. Okay, I think this is actually a really good one though, because we have a lot of things to find, so like we can do a lot of stuff with it. Okay, I need to like draw a picture first. Picture's hardest part. I mean, it's not really the hardest part. The differential equations are the hardest part, but pictures is a hard part. Okay, this is done. Banished. Banished to the homework realm. We need to do... What should we call this? We should call this Mega Problem. Mega Navier-Stokes. That's my title. Everybody likes it. Okay. So it's an inclined plane. It's a liquid flows down an inclined plane in a steady, fully developed laminar flow. Okay, so we've got an inclined plane, and there's a liquid. I guess doing something like that, probably. Well, so what would it look like? The bottom of this liquid is going to have a velocity profile. The velocity is going to be 0, but at the top it's not. So it's going to be something more like this, I guess, but it looks kind of weird. I don't know. I think it's going to be something like that. Like if we were to take a velocity profile, it'd be 0. And this is like a V. Something like that. It's not a thin gap, so it's not going to be linear. Okay. So what do we start with? Well, we always start with conservation of mass. But let's do some assumptions first. So assumptions, our best friends, gets rid of things in our equations. Steady flow, they told us that. They did say it was a liquid, so it's gonna be incompressible. Good. What else have we got? What else shall we assume? Well, they did say that it was fully developed. So fully developed. Oh, we gotta put a coordinate system on here. What do we do? Let's see what they do, actually, because I want to make it the same as theirs. They did X and Y, which is actually what I was going to do as well. Like this. I guess our origin can just be somewhere. It doesn't really matter. So fully developed, that means du dx equals 0. Means the change in the velocity in the x. Now, one thing I will say is du dx equals 0, but I think dv dx also equals 0. So I'm gonna say dv dx, like as in the velocity vector in the x direction. Anywhere we go, it's not gonna change. So our picture actually looks very close to theirs. Yeah. Yeah, and then the only thing that we didn't have is they have gravity going down as well. So we'll say that. Okay, so we got a good picture. It's scary, but I think we need to embark on our journey. So we start our analysis with the conservation of mass equation for a differential flow. You know, just classic, easy I was gonna say Sunday. Today's not Sunday. Holiday type behavior. You know, just doing my conservation of mass differentially. I'm gonna do the big one, and then we're gonna cancel stuff out. Because I think that's just the best way to practice, and also just kind of get our heads around stuff about why things are the way they are. So let's pop out this. And get my... I also have to read up on simility at some point, which, if you were here last time, we were talking about also doing dimensional analysis, or like kind of creating dimensionless groups, like pi groups, and being able to use those for different stuff. And so the next step of that is like, okay, well, we have a pi group model. How do we apply that model to a larger model? How do we extend that model? And that is going to be exciting. I'm going to do that tomorrow, though, not today. Well, not stream tomorrow, but I'm going to be working on that tomorrow. Okay. Where's continuity conservation mass? Here we go. I really should just have this in my supplemental book that I have, but oh, I just picked up all of my notebooks at the same time. That was a big stack. Okay. Alright. 0 equals d e dt. That's steady. Oh, sorry, d rho dt. That's not a p. D rho dt. It's still steady. I'm gonna start writing my assumptions that cancel them out. Will help everybody, I think, including me. And then del dot rho v. So that means that del dot v equals 0. I'm gonna also cancel out this because this is incompressible. Then we have, what is that? So that's d du dx plus dv dy plus dw dz. I'm gonna go ahead and assume that dw dz equals 0. Or ddz, I guess, anything equals 0. That we're not changing across the z plane, which I don't think is super bad. That means the change in the x has to equal the change in the y. That is a good thing. We got some good stuff there. This is a separable... No, it is not a separable. Well, oh, actually, we know that du dx is not going to change. Actually, let's not assume this just yet. Just in case. This is actually going to be 0. Because we already said that it's fully developed. 0 full dev. Then we have, because then that would mean that the change in y has to equal 0, and I don't think that's as easy as that is. So let's see if the book does something different real quick before we move on. So they do say that it's 0. Okay. So we'll say that we do have dw equals 0. ddz, sorry. 0, this is ddz equals 0. Sorry, those are partials. Pretty much everything is a partial. So interesting. So dv dy equals 0. Which means that v equals cy. I feel like that's not correct, though, is the thing. It really shouldn't be... Just from what we know about shear stress, it's like not really gonna be... It shouldn't be a line. And this is assuming that it's a line. No? But they have that. Let's see. Let's do our other do Navier-Stokes. Okay, big chonky boy. Let's do X first, I guess. So it's rho UDT plus U dudx plus V. Oh god, I'll try and make my things a little better. Du dy plus W du dz. Okay, I'm getting it, because this is our V dot del times V. The stupidest operation. And then rho gx. Oh, we actually do have an x. That's kind of nasty, but it's okay. Most of our other stuff is gonna be like fine. Minus dp, so this is actually pressure, dx. Plus mu, and this is our tau, or our shear expression. Plus d squared u over dy squared. I think this is just... Hello, sorry for bothering you. I want to give you viewers. No, it's okay. Don't worry about it, bot. Where's mod icons? Oh, they're here. They're not there. Here we can, there we go. Goodbye. I always think it's funny. It's like, yes, the STEM math guy, please, viewers, I need them so badly. Like, no, dude. We're a bunch of funny little weirdos here. Sorry, you guys aren't weirdos. You guys are great. I'm the weirdos. Okay, we did it. This is great. Let's start canceling stuff out. Anything with time. T equals 0. Not really, but don't worry about it. There's nothing else with time. I tried. Okay. Anything with x, 0. ddx equals 0. Well, yeah, I guess does ddx equal 0, or does, I only wrote dv dx equals 0. So let's see. No properties vary. Okay, so ddx equals 0, that means. Not dv dx. Big difference. Oh, this is so much easier than doing the polar coordinates as my first one. I don't know why I tried to do polar as my first Navier-Stokes example. Oh, crazy. Where's my... Wait, this one is called The Juggler? Oh, this music's called The Juggler? So true. Okay. Sorry, I just got excited about that. This is ddx equals 0. This is ddx equals 0. What else have we got? There's no change in the z either. ddz equals 0. Okay, so what are we left with? Well, we have some gravity left over, we have some rho left over, we have some viscosity left over. That hopefully makes sense, right? Like, okay, our change in our viscosity is going to be proportional to, I guess, the change in viscosity, but like the du dy is probably going to come up in the fact that, I don't know, we'll see. Hi, how's it going? What's up? We're just doing some Navier-Stokes. We're trying to figure out a bunch of stuff about this laminar little flow field that is a thin film sliding down an incline. Doing some differential analysis on it. I don't like this guy. This guy's scary to me, but we're gonna just go ahead with it. I'm gonna just leave all of them. I'm gonna leave Scorched Earth. Okay, that's 0. I just wish I could... If I didn't write them all? What if I didn't write them all? The demons. Okay, so this is gonna be u dv dx plus... Wait, let me check that's right. Yes, and then v dv dy plus w dv dz. That's 0. That's 0. starting to see a pattern. Rho gy minus dp dy, which can change. We don't have anything about saying it can't change in the y direction. It probably should change in the y direction. We have some forces there. Now this one is weird. D squared v over dx squared. I have a question. What is the geometric interpretation of a partial derivative? What does it represent or mean? Yeah, of course. It's a great question. So when we have a space, right? Let's say, I like to think about things in 3D when I'm thinking about multivariable, where these axes don't have to only be spatial axes. They can be like time. They can be anything, right? And so we have like some shape that's in that space that we can kind of relate to. Like maybe it's like something like this. And so what we're saying when we're taking a partial derivative is we're asking how much it's changing in one direction. So if we were to like draw a line down this slope, it's kind of changing. The way that I've drawn it is like if we were to project it onto this side, it's kind of like a little exponential function, right? It's changing like in two directions there. But in this direction, it has a different slope, right? If we wanted to go along the, let's call this the x-axis, the y-axis, and the z-axis, if we wanted to go along this way, that would be a different change. In fact, we wouldn't be changing, right, as we move along that way. So that's all we're saying in with partial derivatives. If we have a space, just what is the rate of change of a specific variable? So it's still the rate of change, but in different directions. Exactly. Yeah, it's like we took a derivative and we just chunked it up basically into like vector components, if you know about vectors, like sort of how we have a vector and it has components, and it's basically all a partial derivative is. And then when you're working with, so like for this kind of stuff, like the reason all these are partials is because we're just saying like, okay, we wanna know about the rate of this function changing spatially. So that's what we tend to use the partial derivatives for. And we're trying to say like, okay, well, it's gonna be affected by how fast you're going in this direction, how much it's changing in this direction. So we have to split all of that up into all of the different variations that it can be, so that we can analyze it like that. And that's why also there's so many things that get canceled out. Because like, for example, this function, this is a curve that's sort of like this, if we were to look at it from the, or this is the assumptions that we've made kind of turn it into this. It's like, oh, you go this way, well, nothing's changing. That's a slope of 0. If you go this way, something's changing. And if you go this way, then nothing's changing also, actually, because we've assumed that these are the same profiles. But yeah, so that's why like we have dx is 0 and dz is 0, because this way nothing changes. Like this velocity here is going to be the same as this velocity here. And then if we go in x, this velocity here, a better example of that, this velocity here is going to be the same as this velocity here. But if we go up, then our velocity is going to get bigger in this case. And then as we get down, it's going to go to 0. There's some cool, 3 Blue 1 Brown has some cool visualizations of that kind of stuff. Okay, thank you very much. Yeah, of course. No worries. I hope it was a good enough explanation. For multivariable in particular, there's a lot of cool stuff you can get with visualizations, just because we can see in 3 dimensions. But then when you get to linear, you start having to kind of be a little more creative with your visual metaphors for stuff. What was I doing? Getting rid of stuff. So yeah, dx doesn't change, dz doesn't change. The dp dy sticks around, this sticks around. Viscosity, oh, I should assume Newtonian. We need it to be Newtonian and laminar. Whoopsies. Almost committed a grave sin there. Definitely need laminar. Definitely needs to be Newtonian. Ooh. And then z, which is not going to give us much, because everything is probably going to go away. Plus u dz dx. Guess what? That doesn't change. plus v dz dz dy. I think... I don't know. I'm gonna leave that one for now. W, this one goes away. Wait, dw dz. Wait, sorry, dv dy. Wait. No, dw. God. Numbers, letters. Hey, how's it going? What's up? This definitely doesn't change. There's no... Thank God there's no gravity in the z direction. I love that. This also goes away. There's probably no shear in the z direction, but like, who knows? Maybe there is. I haven't seen it yet. D squared v over dy squared plus d squared. Nope, that's a w. Got too into looking at stuff and writing down the same stuff. That goes away, that goes away. Okay. Now, the question of the things that remain, what can go away? Been so much better, but I hope some physics can distract me before going to sleep. Oh, that's awesome. Yeah, let's just let the boringness of Navier-Stokes just sink into your skull. I wish you sweet dreams. Sweet dreams of fluids. Okay, I feel like there's some stuff we can get rid of. Those W's are looking, mighty zero-like to me. That actually sounds calming. Yeah, right? Just sink into an abyss. No? Oh yeah, okay, so they do assume W equals 0. We're gonna say W equals 0 as well. I'm gonna write the assumptions that I goofed up in a different color, so I know that I goofed them. I also didn't assume this one at the very start, but I got there eventually. Newtonian I got fully developed as, yeah, they gave me that, so. Okay, so all the W's get to go away. It's gonna be 0. Okay, so I did this equation for nothing. There's literally nothing left in this equation. Oh wait, no, dz dt. Never mind, that also goes to 0. Wait, the whole equation cancels out? Oh wait, no, dp dz. Wait, dp dz stays? Oh, whoa. Are we sure that... I feel like it shouldn't stay. I think we said things didn't change in the z direction. I don't like that. What are we doing? Why is the z still here, babes? Do they use it? They're not using it. They're not using it. Okay. Well, we'll leave it, I guess. Wait, it's dpdz equals 0. It doesn't go to 0, but it does equal 0. That's funny. But if their properties aren't changing in the z, how would we have pressure in the z? You know what I mean? Let's go, gamers. We figured out one component of the pressure field. We did it. Okay. I don't like this VCY. I don't like it at all, and it scares me, and I don't know why I can say V equals CY, because I feel like we should not be able to say V equals CY. But maybe it's because there's a U part that changes. Oh, wait a second. No. It still feels weird. Never mind. I was like, oh, we're tilted, so maybe it's fine. We're gonna add something to it, but we're not. We're not tilted. I don't know, let's just, like, schlonk some stuff around. What have we got? We got rho. Don't question it. If it works, it works. True. It just looks scary. You know when you see something and you're like doing the problem 7 steps ahead in your head and you're like, I don't know if that's gonna be right. I feel like that's where I'm gonna be wrong, and then you end up being wrong and you're like, God, I was right. Fuck. E squared u dy squared. I don't like this differential equation. Well, part of it I don't mind. No, I can't get rid of that. I got excited. Okay, it's a separable differential equation. Do I have to solve this? I feel like I shouldn't have to solve this. I mean, I could solve it with a, what is this? Cauchy-Euler-like? Yeah? I don't think that's the point. I don't think they actually want us to do that. Also, there's no, kind of variables there. After assumption 4 is a plus. Okay, so flow. The continuity equation reduces to dv dy equals 0. Assumptions 3 and 4. V must be constant. Since V is 0, then V must be 0 everywhere. Oh wait, I'm so dumb. Oh my god, guys, I'm so... I was like, it can't be... Of course, V is 0. V is the Y component. Oh my god, I'm so goofy. Oh my god, guys. Okay. Yeah, of course it's 0. Holy moly. Lol. It's okay. That's why we practice, you know? That's why we practice. Oh, look at this. 0. Where else can we get rid of zeros? That's fine, that stays. This is 0. This is 0. Nice, a usable equation. And then the other one is just whatever anyway. Okay, so maybe Navier-Stokes isn't too bad after all. Maybe he is my best friend, if I can just figure out how to assume the right things so that my equation goes to 0, mostly. Which is most of fluid dynamics, really. Oh, we just have to integrate twice? Easy clap. Rho gy minus dp dy plus nothing. Oh, beautiful. Okay. Let's see if we can get somewhere. So dp dy. Wait, what are they asking for us for? I already forgot. Like quantum physics is easier than fluids? I don't know. I think yes and no. So we're looking for velocity profile first. So let's do that. That's gonna be this, I think. So rho gx over mu equals, I guess, the integral d squared u over dy squared, which gives us to separate this properly, probably rho gxy equals du dy. And then the integrals of these equals rho, sorry, there's a constant here. Very important, actually. That's the big thing, like, I really wish people would get on people's cases for that. It's me getting on my case for that. Because I don't do that enough. Plus c1 rho gx, no, sorry, c1y plus c2 equals u. Which is good, that's a parabola, we like parabolas. And then we know that y equals 0, u equals 0. So that means c2 equals 0? Yeah? Mayhaps? Yes. And then, are we given any other information, or is it just say, figure it out? I think the answer is figure it out. Do we have a velocity? Oh, no, h. Wait, do I have to use surface? Not surface tension. Do I have to use... du dy equals... Yes. Yeah, we have to use, whatchamacallit? Evaluating equation 4 at c... Oh, yeah. Wait. At y equals 0 gives... Okay. At y equals h, yeah. Oh, du dy equals 0 at y equals h. Oh, whoa, what? 0 shear stress condition at the liquid free surface. Oh, okay, so that's a different thing, actually. I think I'm gonna have to wrap up soon, unfortunately, but not right now. But we will try and at least get this velocity profile finished. I don't like I don't like writing this. I think this looks bad right now. This looks bad, really bad. It's fine. That was a quick turnaround. Okay, so the thing I need to know is, like, 0 shear stress condition, which I did not know about. Stress at liquid surface. Whoa. So then we say, I guess we use this one then. This is C1. Ah, so rho gx over mu, sorry, gx, over mu y plus c1 equals du dy. Y equals h, du dy equals 0. So rho gx over mu h equals negative. Aha. So our profile is this. Okay, rho gx over 2 mu y squared plus, I'm gonna leave gx just because gx is not, I don't really care that much. We're gonna pop this out. Minus hy equals u. Should we graph it? Let's see, wait, let's see. I'm so excited, actually. We got this, we got this. Okay, that is the textbook, that is not the graphing. Where is this? Oh, there we go. Okay, so these are not right. Okay, so we need to say, I'm gonna say rho g over u y squared, because I want to play around with like seeing how the different variables, minus hy equals x. Ooh, it's gonna be all. Okay, it's going the wrong way? Question mark? Let me see if theirs is the other way. Yeah. Oh, it's because of the gravity. If we say gravity is negative 9.8. Yeah, there we go. Okay, that's not right either. It should be 0 at the bottom. Wait, oh, I guess it is. I guess it is 0 at the bottom. So what's the density of water? Like, okay, so the higher the density is, the more it sort of pulls forward. Huh, interesting. And this is the viscosity. The higher the viscosity, the less it moves forward. That makes sense. And then the higher the height, well, yeah, the higher the height, you know, the higher the height. I guess that makes sense. Let's just check to see. So we had rho g y squared over 2. Y squared over 2. Oh yeah, y squared. I moved my 2 out of the... That's so interesting. I guess it's sort of like... I don't know, I feel like it's a little... I feel like it's a little weird. Well, let's graph theirs too. So theirs is a little, it's just rho g sine theta over mu. So all theirs is adding a sine theta. R. Or let's call it angle, A. Yeah, so the larger the angle, I guess, the more, that's, I don't think about that in my brain right now. And then we have to just find, like, shear stress and stuff. Which I think, okay, I'm trying to think about, so next time, so I'm gonna stream Wednesday. Oh, that's my DMs, sorry. That's my Twitch page. I'm gonna stream Wednesday. I'm trying to think about what we should do. I might not do Fourier series, because Fourier series are kind of like... Okay, it's a crazy thing I was gonna say, like, Fourier series are kind of like trivial, but they're just like, they're like grunt work, you know? They're just grinding stuff, so it's not really some... I feel like I would rather do fluids on stream. I feel like it's more interesting as well. Because I think doing that rotational one next time, it's like finishing up this one, and then trying out the rotational one next time. Oh wait, this one would, or we could, yeah, I think we'll do fluids next time. Because this is kind of the same thing. I was like getting stuck on like, oh, my conservation of mass is like, wait, am I trying to find the velocity profile? No, expression for the acceleration. Oh wait, no, sorry, it wasn't this one, it was this one. Yeah, this one's goofy. Like, I was trying to like figure out what stuff canceled out and I just kind of like didn't do it, so I'll probably just take a whole extra crack at this. I think there's more symmetry stuff we can... I think usually, like, these problems, you're gonna have two of these things, so it's good that we have ddz equals 0 and, like, dd theta equals 0. But I think we gotta keep pushing, because, like... Oh, you can't see it. This is the flow field we're trying to derive, and I did not get there. I got to this, which actually might not be that far off. That's kind of similar to, like, what we had before. Because, like, in this case, we would be solving for v theta. I don't know. It's a little scuffed, though. Also, I don't know I have d squared r... I think we need to go through the cylindrical coordinates. I mean, I can't prove them, but maybe we can find a video of proof that we can watch or something. That'll be on whatchamacallit. Oh, what does Newtonian mean? Okay, so Newton, we have two types of fluids. Every fluid is either Newtonian or non-Newtonian. And Newtonian is a descriptor of viscosity. And so if you have a... wait, I'm pretty sure it's this. I'm just trying to remember if it's only velocity profile. Yeah, so if you have a constant viscosity throughout your entire fluid, then it's Newtonian, and if you don't have a constant viscosity, then it's non-Newtonian. Non-Newtonian fluids are stuff like blood is a non-Newtonian fluid. It behaves sort of differently, but like water is a Newtonian fluid. You know, most liquids that you interact with are Newtonian. It's usually like sort of stuff with phases or microstructures or kind of cool stuff like that. And the reason we assume that is that to be able to use the Navier-Stokes equation, which is this differential equation here, well, this is the insane one. Maybe we look at this one that we just did. In order to use these equations, we're doing conservation of linear momentum stuff. That's all this equation is just like adding up linear momentum. And in order to know the relationship between shear and the derivative in a direction for our velocity in the fluid, essentially, which is like all of this stuff is just velocity, right? Velocity times mass. We have to be able to say what that relationship is. And so for a Newtonian fluid, that relationship is linear, and for a non-Newtonian fluid, it's not. So it becomes a much harder question if you don't have Newtonian fluids. You can't use these. You have to use a different form of the linear momentum conservation. So yeah, and then also laminar is like, I spelled it wrong, but laminar is essentially like saying that we have a flow that we can predict. Sometimes it's like a straight flow, like a lot of the times the flow will be like in straight lines, but it can also be like, you know, flow like that or something. It just means that we know where the flow is going, because a turbulent flow where it's like this and like it just going all over the place and crazy, like you can't really analyze that without doing computational fluid dynamics, and that's a completely different area of analysis. Very cool though. Phobos, I think, is doing some of that. One of the people who is around. Like for heat transfer, for stuff like that, you might be interested in doing that. Although, we also were doing the heat equation in my linear, which is pretty cool. That's like, you have a bar, a one-dimensional bar only, but you can scale it up. And it can bleed heat out the ends only, so heat can either enter or exit through the ends. And you can use Fourier series to create a picture of, you know, how the heat, if this is our initial heat, like Q or whatever, of how that heat like dissipates out, or if you have like you're putting in heat to it like this way, about how that like kind of evens out as well, and then eventually makes a straight equilibrium state at one value. Pretty cool stuff. Pretty cool stuff. You can do a lot with fluids. You can do a lot with math. That's so cool. It's super cool. I think the coolest stuff, I think linear 2, that class that I take, it's like a linear analysis class. It's, I don't know how to describe it. It's kind of like you do differential equations, but like some basic kind of general solutions to differential equations, like methodology of them. And there's just so much cool stuff you can do with differential, like solving, even just doing like series solutions to differential equations. Laplace transforms are so cool, like being able to take a differential equation that's like, you know, like y double prime plus 3y plus 5y equals, you know, sine x cosine x, plus the unit step function at 5 of e to the x, like, and you can just solve that with algebra because of Laplace transforms. Like, that's crazy awesome. Well, maybe not this, but if you said sine x plus cosine x. It's super cool. Super cool stuff. Really useful. I mean, I like stuff like Navier-Stokes a lot because you actually get to use the math that you learn, like, for the first time in forever. Oh, that's my curl explanation. And, where did my Navier-Stokes go? Did I put it at the top? Wait, where did it go? Oh, here it is. Like, all this stuff is, like, it makes so much sense when you, like, when you're learning it in math and you're like, man, I gotta do, like, directional derivatives, I don't know what I'm gonna use that for. And then you go into fluids and you're like, oh, total acceleration is a spatial acceleration and a time acceleration. And you're like, I got it. I figured it out. Holy shit. So beautiful. Alright, I'm down to answer, like, any questions if people have questions, but I think I'm gonna head out if not and get something to eat. Teehee. And I'll be back on Wednesday. Not same time. Wait, actually, yes, same time. I think I'm gonna try and do, like, these earlier streams, because I think they work well for people, and they work well for me. And I like them, so yeah. Let's go raid Rev. I think Rev is still streaming. Is Rev? No, is Rev not streaming? I'm gonna be so sad if Rev is not streaming right now. Wait, no. Wait, am I just not following Rev? Maybe I'm not following Rev.
Yeah, pre-ordering games was because...
Wait, Rev is... Yes, we're gonna raid Rev. Okay. This is my friend Rev. Rev is awesome. And he's playing Hypnospace Outlaw, which is a really cool game about being a moderator on the internet. And everybody go give him some love because he's great. He's not doing math, I'm sorry. I'm the only one out of the people who I stream with who does math. I will see you guys on Wednesday. I hope you have a great day. And thanks for hanging out. It was great. It was really nice for you guys to stick with me through all my insane fourier series. Thanks. Love you guys. Bye.
Oh, Damie. Hi. Thank you for the raid, Damie. I'm playing